What's up guys? Hello, welcome back everyone to my chemistry classes. You know what? Today I won't be teaching you anything in chemistry. And you'll be like, okay, so if you're not going to teach us chemistry, what you are going to teach us? So I am going to tell you the tricks for drinking cold drink. You must all of you would have this problem, right? Your mom will be shouting in the kitchen. See, you are sleeping and suddenly you felt like drinking cold drink, right? And thus you went towards the fridge and then your mom will start shouting, do not open the bottle. If you are opening it, close it very tightly. Don't keep it out of the fridge. Go keep it inside. Blah, 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 right? All moms do that because I don't know why they are in love with cold drink and why they hate we people drinking cold drink, right? You know why this is so? Because our moms are very intelligent. They are far more intelligent than us. They are very, very good chemists. So these people, these moms, they already know a concept, and the concept is the solubility of gases in a liquid. Solubility of a gas in a liquid. So this is the concept that we are going to study. So if your moms are there with you, you can call your moms also, because now they can understand the lecture very nicely, because moms are intelligent in this topic. So you know, right, gases, they do get dissolved in water. For example, I am very bad in drawing, but let me draw a cute little diagram of a fish. I think this looks like a fish, right? Oh wow, it's looking nice, right? Let's say the fish is there in water. In bio, we studied something related to gills and all, I don't remember. But there was this topic, right? So the fishes also breathe in the surface of water, right? I don't know how they breathe, but there is something. I have seen fishes, when they come out, they'll take the gases and then they'll release the gases. Something like this is there, right? So how are fishes and other animals in the water sustaining, right? That means there must be some dissolved gases. Right? So if the gases would not have been dissolved in water, we could have said that, life of a fish would not have been there. Not only this, so that means gases actually dissolve in liquid, and hence the topic I have written, the solubility of a gas in liquid. So you do understand that gas can be dissolved in liquid. Not only this, you people must have heard about carbonated drinks. I really like cold drinks. So a Pepsi bottle is something, again I'm bad in drawing. So let us consider this to be a bottle of Pepsi, okay? So what is Pepsi? Why your mom always says don't drink too much of Pepsi and all. So this is nothing, but this is a fizzy liquid, right? So it is carbonated water. And what is carbonated water? Carbonated water simply means that lots of carbon dioxide is dissolved in water. So guys, when we breathe, right, we take in the oxygen and we release carbon dioxide. So suppose if I am taking a glass of water and I start releasing all the carbon dioxide into the water. So do you think it will become carbonated water? Do you actually think it will become cold drink if I am simply taking a glass of water and I am doing no, right? That's not possible. So why is it that when you drink cold drink or carbonated water, you could feel a fizz, but when you're simply releasing carbon dioxide in water, you don't feel anything. It's of no use. That means now you could have decoded that, ma'am, when we talk about the solubility of a gas in a liquid, it must be based upon certain factors, right? So there must be certain factors which will decide the solubility of the gas in a liquid. And what are those factors which are going to decide the solubility of the gas in the liquid? The very first factor is nature of the gas. Coming on to the second factor, temperature of the system. And finally, let me come on to the third factor, and this factor is something related to pressure of the system. Fine. So let us discuss these three factors one by one in details and how they are actually responsible for the solubility of a gas in the liquid. Guys, do you know like dissolves like? Have you heard of this principle? This principle is there, right? Moreover, this is something like is in love with like. So something which both of them are approximately the same, then they'll dissolve easily in each other. The same kind of principle is utilized when a gas is being dissolved into water. Listen to me, for example, very carefully. Let's say I am taking nitrogen gas. The solubility of all the gases in water is literally different. How much? Suppose I have taken 1 liter of water at, let us say, 4 degrees C, and let's say at 3 atm pressure. Okay, and I am having so many samples of gases. First I am having nitrogen, I have O2, I have CO2, I have ammonia, let us say I have CCl4 and so on. Fine. Now the amount of a particular gas that can be dissolved in a given amount of liquid at a given temperature and pressure condition totally depends upon the nature of the gas. You know, right, water is polar. It is aqueous in nature. So any particular gas which has a tendency, to form a kind of bond with water will have more tendency to be dissolved in water. Whereas any particular gas which has very less tendency to dissolve in water, maybe because of its high, breaking the energy. For example, N triple bond N. Lots of energy is required to break it, but we are not breaking the molecule. I just want nitrogen molecule to mingle up in the molecules of water. So after this mingling up which is taking place, if these bonds are coming out to be stronger, then we will say that solubility of that gas will be higher, otherwise the solubility of the gas will be a lower value. Right? That means which or what kind of gas is being dissolved in water is typically dependent upon the nature of the gas, and the nature of the gas is directly going to determine the solubility of different gases in the liquid. Fine enough? Now let us move on to the second terminology, which is the temperature of the system. Do you agree? Okay, listen to me. Let me start from the beginning itself. Let us say there is a container in which water molecules are there. Okay, and the carbon dioxide is freely moving into it's freely there on the surface, into the atmosphere. So they are more free, and everyone wants to be free, right? Now you want that the molecules should lose their energy and they come and settle down into the pores of water. So you want, rather than these molecules going in the upward direction, they should be coming and settling down into the water. Right? So this is what we want. Now if you want this thing, don't you think you have to decrease the energy of the molecules? right? So I need to decrease the energy of the molecules, then only the molecules will come and settle down into the pores of water. Until and unless you decrease their energy, they would not have tendency to come and settle down. Why? Because when they are settling down in water, they are actually losing their entropy, right? Otherwise they were so random. So in order to dissolve a gas in the liquid, you need to make sure that you are decreasing the energy of the molecules, right? But listen to me carefully. Suppose I start heating the system. If I start heating the system, don't you think I am providing more energy to the molecules so that they can escape? So if you heat, the molecules which were already, dissolved, they are moving out, they are escaping out. So can I now say that increase in temperature, increase in the temperature will decrease the solubility of the gas. You start increasing the temperature, increase, the solubility of the gas will be decreased. Okay. So can I now simply say that the solubility of a gas is inversely proportional to the temperature of the system, not the temperature of gas. It is totally the temperature of system, which includes both the solvent and the gas. Right enough? That is why in summers, your mom will generally ask you to go and keep the bottle of a cold drink in the refrigerator, because the more the lower will be, or let us say the more lesser the value of temperature will be, the molecules will lose their energy and they will settle down into the bottom of the container. Fine. You keep the bottle of cold drink outside and all the CO2 so absorbed will get released and hence it will become useless. Point number 1. So this is also clear. The temperature of the system is also going to decide the solubility of the gas in a liquid. Okay, so finally I need to move on to the pressure of the system. So the third point is pressure of the system. So let's see what is there in the pressure of the system. Do you agree that the more will be, suppose the bottles, see you would have seen any bottle. So see, for example, I need to dissolve CO2 in water. So this is all water. Okay, and I am putting the molecules of CO2. Now CO2 molecules have the tendency to go away, right? They have the tendency to go away. But suppose if I seal it and I am storing it under a very high pressure. So you are applying high pressure from outside. You have sealed it. So don't you think the gas will be soluble? However, see, because when you put the pressure from outside, increase the pressure, the molecules will be forced to dissolve in the water. The molecules will be forced to go into water. Right? But if you open it, if you try to reduce the pressure, you would have seen, right, a bottle of cold drink. If you open, there will be a fizz. Why? Because already the gas was stored in the bottle at a very high pressure. As soon as you open the lid, the pressure will be released, and when the pressure will be released, all the CO2 which is dissolved in water would have the tendency to come out. Right? So this is the third thing where I can say pressure of the system. So I could have written it like solubility is going to be directly proportional to pressure of the system. So increase the pressure of the system and I can easily say that the solubility of the gas in the system will increase. Am I right? So guys, this was all about the introduction of solubility of a gas in a liquid. Right? This was just in the layman's language. Now scientifically there was a person who was known as Henry, and he has given certain laws which are known as Henry's law. So let me tell you what this person Henry said. Let us try to see what were the postulates given by Henry's. So this person Henry, he actually started his discussion Henry started his discussion by discussing the dissolution of the gas in the liquid. So the title was this only. He was studying the dissolution of the gas in the liquid. Now listen to me very carefully. Henry was very smart guy. You know what he did? He did his discussion in two different steps. First he said that I am a kid. So I am a kid means I'll be doing very simple things, right? I'll just play with the soft toys and I'll be like very kiddish things I'll do, right? So now not kiddish, but what he did, he called it as elementary Henry's law. Elementary Henry laws mean the one which were given in the initial stages, the most simplest form of Henry's law. Okay. Now what was discussed in elementary Henry's law? He has just taken the dissolution of only one gas in the liquid. So he said, give me just one gas and I will be dissolving the gas in liquid, and I'll try to find out what are the special cases, what could be the mathematical and the conceptual approach. Fine. So this was the first statement he has given. Then we have another version of Henry's law which was given as advanced Henry's law. So the second one which was given was known as advanced Henry's law. And in the case of advanced Henry's law, he said that multiple gases were considered to be dissolved in the liquid. So these are the two things that we will be studying in details today. Fine. Now guys, listen to me very carefully. Whenever we are doing the experiment for the dissolution of a gas in the liquid, you need to make sure that the temperature of the system has to be kept constant. Temperature must be kept constant. And now you might be like, why so? Listen, no. For example, you are comparing that am I a good chemistry teacher or not, right? Suppose you are comparing me whether I am a good chemistry teacher or not. Yeah, when you will be comparing me as a teacher, you should be comparing me with another chemistry tutor, right? Because the subject has to be the same. The chapter has to be the same, then only you will do the comparison whether ma'am is good or not good, right? Whether ma'am goes for question answer or she doesn't go. Whether ma'am explains everything nicely or she doesn't explain, right? This is not possible, right? That you will be comparing ma'am with some other sir, let's say who is of another subject, and let's say who is teaching only and only question answers, right? So maybe I am teaching one chapter if you need to compare me, you need to make some standards. You need to make some things which are like basics. Keeping these things constant, now find out which one is better or which one is bad, right? Similarly, suppose I am studying the dissolution of CO2 and O2, and for both of them I have taken 1 liter water. Here also I am taking 1 liter water. Now whether more of CO2 will be dissolved in water or more of O2 will be dissolved in water will typically depend or can simply be compared when you are keeping the temperature same. Let's say here also you kept 20 degrees C. Then you can compare and the values will be okay, right? But suppose you said no, I will take CO2 at 10 degree and I will take O2 at 80 degree. So I'll say you are a fool comparing the two things, right? To compare, you need to make sure the other factors have to be kept constant. Fine? So similarly, Henry also said that the temperature will be kept constant during the entire experiment. Okay? Now what happened? See carefully. It was found that if I am talking about the Henry's law, it was based upon a general observation. So if I am talking about Henry's law, there was a general observation and it said that suppose there is a container which is containing some solvent. Okay, there is a container containing some solvent. I am keeping the container on a shelf, let's say, and I am enclosing it with some cover like this. Okay, and I am trying to impinge one particular gas inside the system. Right? I am impinging some gas inside the system. So let us say the gas molecules will go. Now the gas will be spreaded here. So the entire surface will be covered, entire volume will be covered by the gas. Right? So that means there must be some pressure of the gas, I am enclosing it. Clear enough? Now suppose I am saying that the temperature of the system is kept fixed. Don't you think if I want you to find out how much gas is actually going into the surface of water and how much gas is actually getting collected in the surface of water, so I can say the mass of the gas dissolved in solvent the mass of the gas that is dissolved in the solvent has been found to be directly proportional to the pressure of the gas. With which the gas was, pushed into the system. See, if you are pushing the gas with lots of pressure, so lots of pressure means lots of molecules will want to go inside the system, right? So the mass of the gas that will be dissolved will be found to be directly proportional to the pressure of the gas. Okay, let me write like this. So this is the mass of the gas which is going into the liquid, whereas P gas is the pressure of the gas above the surface of the liquid. Okay. Now see, when you will remove the proportionality sign, you will get M is equal to some K into P gas. Okay. And see, I have seen so many students getting confused. They say that this K is nothing but Henry's law constant. No guys, it's just a proportionality constant and this K has got nothing to do with Henry's constant. The vapor pressure of acetone at 20 degrees C is 185 torr. So let me just write down the points. So P naught of acetone is 185 torr. Okay, and yeah, the temperature is mentioned as 20 degrees C. Now he is saying that when 1.2 grams of a non-volatile substance, so let us say the mass of non-volatile substance is 1.2 grams, of a non-volatile substance was dissolved in 100 grams of acetone. So the mass of solvent is 100 grams. Again, the temperature is given to me as 20 degrees C. Its vapor pressure was found to be 183 torr. So pressure of the solution was 183 torr. So you need to calculate the molar mass of the substance. The question is really good and easy also. So as per you can see from the data, I just have to talk about the relative lowering of vapor pressure. So we know P naught of acetone minus P of solution divided by P naught of acetone. So the relative lowering of vapor pressure is directly proportional to or is equal to the mole fraction of solute. Right? So now we just need to solve it out. So I have done the calculation for you. Let me just write down the points. So this is 185 minus 183 by 185 is equal to 2 divided by 185, and this is the mole fraction of solute. Right? So once again, if I write down 2 by 185 is equal to the given mass. So the given mass is 1.2 divided by, okay, so the better thing I should have done is I should have used the calculation of, so this is the mole fraction. So I should first have written the formula, the number of moles of solute by the number of moles of solute plus number of moles of solvent. Okay, acetone you already know could be written as CH3CO CH3, and the molar mass of acetone will be 12 into 3 because 3 carbons are there, 1 oxygen is there, so 16 into 1 plus 6 hydrogens are there, so 6 into 1. So this all if you do, so this all will be giving me the molar mass of acetone. Okay. So if I write down the number of moles of acetone or solvent will be equal to the given mass, which is 100, divided by the molar mass of acetone that I already know. Clear? Now if I solve this further, what I'll ask you to do, so this is done, 1.2 you just need to take into account. Then I'll solve it. So 2 by 185 is equal to number of moles of solute by number of moles of solute plus number of moles of solvent, which is 100 divided by molar mass. This complete thing you know, you can easily solve out the value of n, right? Once you can solve out the value of n could be written as given mass by molar mass of solute. So you know the value of n, you know 1.2, you can easily calculate the answer for the molar mass of solute. Let me check the answer, and the answer that you will be getting will be 64 grams per mole. Okay, so this is the answer, and our option number B will be the correct option for this particular question. Okay, so guys, this was our question number 1 that we had chosen as the JEE Mains question. Now we need to move on to question number 2. So how I should be moving on to question number 2, let us see that into account. So question number 2, before giving you the question on screen, let me just prepare the board. So you read the question by the time I'll prepare the board more. So the question says that a molar solution, so this is a very simple question, you do not have to do any of the calculation, it's just And you know what, this is a past year JEE Mains question. It has been asked in JEE Mains some years back. So the question says, a molar solution is one that contains 1 mole of a solute. So he is just asking you to define what is 1 molar solution. So you know, right, 1 molar solution is 1 mole of solute is to be dissolved in 1 kg of solvent. That is what is the definition of molar. So see, 1000 grams of solvent, okay, is nothing but 1 kg of solvent. 1 liter of solvent, no. 1 liter of solution, no. 22.4 liters of solution, no. So directly coming to the answer, option number 1 is the correct option for this particular question. So see, this was also an easy and a scoring question. Now having done with this particular question, let us move on to our question number 3. Question number 3 says, for a dilute solution, the Reol's law states that. So what is Reol's law? So he is talking about relative lowering, right? So you know, right, that relative lowering of vapor pressure is equal to mole fraction of the solute. That means P naught minus P of solution divided by P naught is equal to mole fraction of solute. Let me start reading each and every option and then we'll see. So he is saying for a dilute solution, the Reol's law states that the lowering of vapor pressure, no. Reol's law is basically concerned about the relative lowering. So A is not the correct option. The relative lowering of vapor pressure is equal to the mole fraction of solute. That is correct. Let's read the third statement. The relative lowering of vapor pressure is proportional to the amount of solute in the solution. Although I agree it is proportional, but the final statement of Reol's law was that it is equal to the mole fraction of the solute, right? Like we cannot say more will be the, so simply talking in terms of mass will not give me the answer. And the third, the D part is the vapor pressure of the solution is equal to mole fraction of the solvent, totally a wrong option in terms of Reol's law. So for the Reol's law, the obvious statement is option number 2. Fine. Once again, an easy and interesting question. So this was our question number 3. Now we need to move on to another question, which is question number 4. Okay, so this is our question number 4, and the question says that consider separate solutions of, so there are a few solutions which are given to you, you have to consider separate solutions of. First is 0.500 molar ethanol solution. Okay, cool enough. Then is 0.100 molar, so point number 2 is 0.100 molar Mg3 PO4 twice aqueous solution. The third that is given to me is 0.250 molar KBr aqueous solution, and the fourth solution that is given to me is 0.125 molar Na3PO4 aqueous solution, and all the solutions are given at the same temperature 25 degrees C. So he is saying which statement is correct about those solutions, assuming all electrolytes to be strong electrolytes. So when by himself he is saying that all the electrolytes that have been given to you are strong electrolytes, that simply means first of all you have to take into account the Vance-Off factor. So the Vance-Off factor for ethanol is 1, because ethanol is an organic substance, it will not undergo dissociation in water, like not 100% dissociation. Moving on to Mg3PO4 twice. So we have Mg3PO4 twice will form 3Mg2 plus 2PO4 3 minus. So making it a total of 2 plus 3, 5 ions, right? So if Vence-Hoff factor is 5, so 5 ions will be obtained. So what will be the overall concentration? The overall concentration will be 5 into 0.100. This implies 0.500 molar. So it appears as if the particles are having a total concentration of 0.500 molar. Now moving on to KBr. From KBr you can say what is Vence-Hoff factor? K plus plus Br minus. Vence-Hoff factor is 2. So making it the overall solution appears to be 0.500 molar. And then we have Na3PO4. So we will have 3 times Na plus PO4 3 minus. So a total of 1 plus 3. 4 ions are there. So when 4 ions are there, multiplied by 4, making it a total of again 0. Okay. Now you talk about any of the colligative property, whether it is elevation in boiling point, depression in freezing point, osmotic pressure or relative lowering of vapor pressure. They were directly dependent upon the total number of particles in the solution, right? So since the total number of particles in the solutions are actually having the concentration 0.500, 0.500, 0.500, 0.500, the concentration in all the 4 cases is same. So when I am saying the final concentration in all the cases is same, so I can simply say that they all will have the same value of osmotic pressure. Okay, so this is correct. Let me still read all the options. 0.100 molar Mg3PO4 twice has the highest osmotic pressure? No, same as others. This much has the highest osmotic pressure or this has the highest osmotic pressure? No. So the only obvious answer is that since all of them are having exactly the same value of the total number of particles in the solution, so I can say that they are having the same value of the colligative properties also. Fine. So this was a pretty simple question. Now having done this question also, we can move on to question number 5. Let me prepare the board and then we'll come on to the next question. And question number 5 says, when mercuric iodide is added to aqueous solution of potassium iodide, let us see, mercuric iodide, HgI2. So see, mercury exists in 2 oxidation states, mercurous, mercuric. So mercurous is plus Hg plus 1 and mercuric is Hg plus 2. So we have mercuric iodide HgI2 is added to an aqueous solution of potassium iodide Ki. It will be leading to the formation of K2HgI4. So a complex is formed that you must be knowing. Okay, so now I will say when mercuric iodide is added to an aqueous solution of Ki, it will form K2HgI4. Let me just balance. This is the balanced chemical equation that I will be getting. So we have Hg, 4 iodines, 2 potassiums are there, and here also we have the same thing. So we have K2 HgI2 plus 2 Ki to form K2HgI4. Now my question is, what will happen? Whether the freezing point will increase or the freezing point will be lowered, the freezing point doesn't change and the boiling point doesn't change. So for sure I will say that when you are adding, so see, let us say this Ki, which is an aqueous solution. Now this aqueous solution is there. So you are getting the molecule. So earlier what was the Vence-Hoff factor? If you can see, the Vence-Hoff factor, the total number of ions in the solution are changing. Now see how many ions are there. You will get 2 potassium plus HgI4 2 minus. So 1 ion plus 2 ions. Now you are getting a total of 3 ions, right? So since you are getting a total of 3 ions, let us figure out earlier how many ions were there. So earlier you had 2 potassium, 2 iodine. So earlier you were having a total of 4 ions. So now, and HgI2 was not ionic, it was not getting dissociated. So now you can see, since the number of ions in aqueous solution is changing, so the freezing point will change as well as the boiling point will change. So these options are saying they will not change, it's a wrong answer. Now see, since we know that, so see, we already know, no, that delta TF is equal to Kf into molality into I. So since I can say that number of ions in the solution is decreasing, so I will simply say that there will be an increase in, so you can simply say that the freezing point will be raised. Okay. So this is the final answer to this particular question, that the freezing point will be raised when HgI2 will be added to an aqueous solution of aqueous Ki. Okay. So this was our question number 5. Now we need to move on to the next question, which is question number 6. So moving on to our next question, question number 6. It says that during the depression of freezing point. So we know, right, when a non-volatile solute is added to a volatile solvent, there will be elevation in boiling point and there will be depression in freezing point. So during the depression of freezing point in the solution, the following are in equilibrium. So when something is freezing out, let us say you have a solution, okay, where some non-volatile solute is added to the volatile solvent. Okay. So you can say that you have aqueous solution of NaCl, where NaCl is the solute and water is the solvent, and you are freezing it. So genuinely we will not be considering the freezing of solute, we will just be saying the liquid solvent, the pure liquid solvent will now be coming in equilibrium with the solidified solid solvent. So he is saying which of the following are in equilibrium. Let's start from bottom. So he is saying the liquid solute and solid solvent will come in equilibrium. No, I am saying whenever freezing will be done of solvent, not of solute. Liquid solute, solid solute. Again, there is nothing to be talking about solute. Okay. Then liquid solvent, solid solute. So wherever you see solute, it's not the answer. Liquid solvent, solid solvent, correct answer. Okay, so this is how option number A could be taken as the correct answer for this particular question. Okay, so this was our question number 6. Now we need to move on to the next question, which is our question number 7. So here there is another question, question number 7. The question says that the molecular weight of benzoic acid in benzene as determined by depression in freezing point method will correspond to what? Now see, so I am saying there is a depression in freezing point when benzoic acid is taken in benzene and there is a depression in freezing point. Now see, why is there a depression in freezing point? Now you know, right, this thing we have already done in organic chemistry also, that this benzoic acid will combine with another molecule of benzoic acid in the presence of benzene as solvent. So see, when you will be taking benzene as solvent, it will combine with benzoic acid and it will lead to the formation of a dimer. Okay, so it is basically because of dimerization that the number of particles, so I will be 1 divided by 2, you can take I as half. So see, so there is a depression in freezing point because of ionization of benzoic acid, no. Dimerization of benzoic acid, yes, it doesn't form the trimer, and no solvation also. Okay, so solvation will be when benzoic acid will be added to water, but right now benzoic acid is added to benzene, so it will just form a dimer, and thus because of the dimer formation there will be a depression in freezing point. Okay, so this was totally related to our question number 7th. Now let me once again prepare the board so that we can move on to another question. Which is our question number 8. So, to show you the question number 8, the question says, the freezing point in degree C of the solution containing, so there is a solution which contains 0.1 grams of K3FeCN6, very nice, the molar mass is given to you as 329 grams per mole and it is prepared in 100 grams of water. And the Kf of water, since you know, is water, so 1.86 Kelvin kg per mole. Okay, now see, we can say that, so this is given to me, now he has asked you to calculate the freezing point. Okay, so we know, right, we can simply write delta Tf is equal to Kf into molality, but please do not forget to take into account the Venshoff factor I. Now delta Tf I need to calculate is equal to I. Now what is K3FeCN6? So when you will take an aqueous solution of K3FeCN6, this will lead to the formation of 3K positive plus FeCN6 with a negative. So making it a total of how many particles? 3 plus 1 divided by 1, so 4. So value of I will be 4 into 1.86 Kelvin kg per mole divided by molality. So molality is basically defined as given mass divided by molar mass by mass of solvent in kilograms, right. So if you do the calculation, so let's see, this is kg, so this is kg, this is gram, this is gram, this is per mole, this is per mole. You solve, you will get delta Tf is equal to 4 into 1.86 into 0.1 into 10 to be divided by 329 Kelvin. Okay, and now you know, right, so the water, simple water will freeze at 0 degree C or 273 Kelvin. So for this question number 8, if you solve it, you will be getting the answer. So one more thing which you can take into account, this delta Tf could be taken in degree C also because it is just the difference. So on solving, you will get the value of water of the freezing point as minus 2.3 into 10 raised to the power minus 2 degree C. So this is the freezing point of the solution. Okay, so we have the options minus 2.3 into 10 raised to the power minus 2 degrees C. Fine. So this is how we could have solved our question number 8 also. Fine. Now, since we are done with question number 8, we are left with 2 more questions. So, let me first prepare the board for another question, which is question number 9. So, let us move on to the next question, which is question number 9. This says that the elevation in boiling point, that means delta TB, when 13.44 grams of a freshly prepared CuCl2 aqueous are added to 1 kilogram of water. And so you need to just tell me what is the elevation in boiling point, and the molecular weight of CuCl2 is given to me as, so there must be some, it should be 134.4 grams per mole, and the Kb is also given to you. So that's it, you need to do the value of delta Tb, which is simple again. So you can say delta Tb is equal to I into Kb into molality. My humble request, please don't forget about this I. So since CuCl2 is ionic, it can undergo dissociation to form Cu2 plus 2Cl minus. So the value of I will be 2 plus 1, 3. Okay, and if I substitute the value delta Tb, I need to calculate. So 3 into Kb is 0.52 Kelvin kg per mole divided by molality. Now molality could be given as given mass 13.44 grams by molar mass by mass of solvent in kg, which is 1 kg. 1 kg, kg, so per mole, grams, grams, you can solve it and you can simply get the elevation in boiling point, which is delta Tb. So if you want me, I can check out the answer for this question, and so this particular question will have, so the elevation in boiling point when this gram of this, so the final answer will be coming out to be 0.156. So you can approximate to 0.16.